In this video tutorial, we will look at digital filters and how they can be used to reduce noise contamination in recorded data. From the Analysis menu, Digital Filters option, you can select between two basic types of filter, Iir, Infinite Impulse Response, and FIR, Finite Impulse Response. Here I am displaying two data files showing the effects of the filters on raw data. FIR filters generate coefficients and use these to calculate the filtered output based on the data both before and after the current data point. Because they use past and future data, they introduce ringing effects both before and after transients in the data. FIR filters introduce a constant delay which Spike2 arranges to be 0. Consequently, FIR filters do not shift peak and trough positions. Iir filters are representations of standard analog Butterworth, Bessel, Chebyshev and resonator filters mapped into digital form. These types of filter are causal. They only use data before the current point to calculate the output. This means that they do not suffer pre-ringing effects due to sharp transients. But they introduce a phase delay which changes with frequency, the result of which is that the positions of peaks and troughs will change. Now that we've seen the main differences between the filter types, let's look at applying filters to our raw data. By selecting the FIR filter option from the Analysis menu. The filter dialog displays an oscilloscope view showing a section of the waveform taken from the current x-axis position of the data file, along with a drop-down list that holds a filter bank of examples that can be applied to the data. The data display in the dialog changes to show the effects of the selected filter in the standard waveform color, with the original unfiltered data shown in grey. If we uncheck the same scale option, the filtered data is scaled to fit the display window, and we will be able to see the changes in amplitude between the raw and filtered output on the right-hand axes. The filter bank drop-down holds a list of examples for quick access, but we can also define our own filters by setting up an arrangement of bands for passing and stopping frequency ranges. Clicking on the Show Details button extends the dialog to show a range of filter settings that can be edited directly. The style of filter you want to create is selected from the drop-down Type list in the dialog. This includes differentiator filters, as well as the standard low and high pass and bandpass filters. Differentiators are only made available for FIR filter types. The characteristics of your chosen filter are shown in the graphical display on the left-hand side. This shows the frequency range up to half the sample rate of the raw data on the x-axis. Pass bands, stop bands, and transition gap settings of your filter can be edited by clicking and dragging with the mouse, or you can edit the settings directly in the appropriate fields of the dialog. And click the Set button. FIR filters use a set of coefficients to calculate the filtered output. With the Auto checkbox enabled, Spike2 automatically adjusts the coefficient setting to produce a useful filter. You can make small adjustments to increase or decrease the number of coefficients using the slider below. But large changes can easily produce unstable filters. The traffic light system above the slider displays a green light if the filter is good, amber if the result is not ideal but still usable, and red if the result is no good at all. Other options in the dialog allow the display of gain in dB or linearly, and display the logarithmic frequency. Once you are happy with the filter settings, we can apply the given filter to the data using the Apply button in the dialog. Filtered output can be written to a new free channel in the data file or a memory channel as waveform or real wave data. Real wave data gives a more accurate result but takes up twice as much space in the file. Leaving the rescale box checked sets the output scale and offset to give the best representation of the data as a 16-bit integer waveform. Clicking OK then writes the filtered output to the file. Full technical details of the filters and all of their settings can be found in the online help. You can save your new filter back to the filter bank in the top of the dialog. Simply rename the current selection and when we close the filter dialog, we will be given the option of adding our newly created filter to the current space in the filter bank. You can also load and save whole filter banks using the buttons in the dialog. Click Close and then select Yes to add your new filter to the bank. Double-clicking on the y-axis and selecting Optimize shows us our filtered data. We can also give our filtered data a title by double-clicking on the channel name. Now let's apply an Iir filter. The main Iir filter dialog is the same in appearance as the FIR. Selecting log frequency for Iir filters displays the filter characteristics in a more common form. Filters can be based on Butterworth, Bessel or Chebyshev filter models. Resonator and notch filters can be used as very narrow bandpass and bandstop filters. The graphical display shows the changes in the steepness of the cutoff and the passband for each filter model. Unless you know that you need a different model, you should use a Butterworth filter. By clicking and dragging the bands, we can set up our filter much like before, or edit the corner frequency directly. The order setting determines the sharpness of the filter. This is equivalent to the dB per octave setting seen with analog filters. We can give our new filter a title, and then click Apply and OK to write the filtered data to our file. Closing the dialog will again give us the option of saving it to the filter bank. Again, we can optimize and title the channel. The best type of filter to use depends on your data and the noise or frequencies you are trying to remove. When filtering data, it is always a matter of finding the best compromise between removing the unwanted frequencies while preserving as much of the signals of interest as possible. I hope this video has given you an insight into how to use digital filters to remove noise from your data. In our next tutorial, we'll be looking at how to remove mains hum and other artifacts using more advanced scripting methods.